electrochemical process. And then we have a series of plateaus all the way down. Okay? So now, this one, at point 8, is related to the decomposition of the electrolyte. This will be clear later, but as I said you before, this graphite is not stable with conventional electrolytes. So we have some decomposition here with the formation of a film, as we will see, an SEI. And then you see that these curves proceed with these various plateau, because if this is the schematic structure of graphite, you see these are all graphene layers. Lithium doesn't go into the layers in a disordered way. In other words, not one lithium goes here and the other one doesn't go here or here or here. But first the lithium fill up one layer and then some other layer and so forth. And you see that we have various stages. So this is stage 4, 3, 2, or 1. And these numbers are related to the empty layers. So you see in this case, first case, we have filled this layer, fill up this one. There are 4 empty layers in between. And this is stage 1. Stage 4, which corresponds to this plateau. Then when this is finished, some other layer is going to be filled up, and the separation between the filled empty layer is 3 empty layers. So this is stage 3 here. Then stage 2, and then stage 1. The stage 1 corresponds at the maximum composition. So that means 1 lithium equivalent for 6 carbon. So all this, this is, of course, is not the stage 1. Stage 1 will be when all this graphene will be filled up with the 1 lithium equivalent. And you see that here this is a bit unprecise because these curves are a bit lower, and in average we have 50 millivolts versus lithium. Okay? Let's see what time is it. Okay. We're almost there, come on. Okay, here you see what we are talking about. This graph is very important because it's reporting the stability domain of an electrolyte. What that means? The stability domains indicates the voltage interval, voltage range, while an electrolyte is stable. For instance, if we take water, we have this kind of level. The lower potential is 0, and this is a reduction potential, which corresponds to reduction of hydrogen. And the oxidation potential is 123, thermodynamically, of course, which correspond to okay? So we better do like this. Okay? What that means? That means that if we have an electrode couples which operates between 0 and 123 volts, then water can be used. But if we have an electrode couple which operates above or below this interval, water cannot be used. In fact, as I told you before, if we try to use lithium in contact with water, since lithium has a voltage of 3.01 up here, they immediately react with water, forming hydrogen and oxygen. So this stability domain, it tells us which are the voltage that can be, which are the electrodes can be used with a given electrolyte. And this electrode can be within the stability domain. So now this red part here is the stability domain of a normal organic solvent electrolyte that you use in lithium-ion batteries, maybe this electrolyte. LiPF6 in a mixture of ethylene carbonate and dimethyl carbonate, very common. Okay, so this electrolyte has a voltage, reductive voltage, which is about 0.8. This is versus lithium. And up here, we arrive about 4.5 volts. Okay? So, thermodynamically, only electrodes which are within this interval can be used. But graphite has a voltage, as I showed you before, as we discussed before, down here to about 0.05. So thermodynamically, speaking, graphite cannot be used with this electrolyte. Okay? But if even if there is a thermodynamic instability, we can increase stability kinetically. What that means? That means that when, you see, as we saw before, well, can go back here. You see, what will happen? Then when the potential of the cell reaches 0.8, namely this value, the electrolyte decomposes because it's below the stability limit. And by decomposing, however, it forms a film which deposits on the surface of the graphite electrode. So we will have now that this again, as in the case of lithium, if this is a graphite electrode, we will have the formation now of a film, which is called SEI. And as we will see, this film is formed by inorganic compounds. And this film is electronically insulator. So if you have a film which does not allow electron transfer, the decomposition reaction stops. And this is why this is called protective film. However, this film has enough ionic conductivity to let lithium to go in and out. And this is why it's called solid electrolyte interface. Actually, as we will see in the next lecture, in other lectures, in the future, also the cathode material, most common cathode material, operates outside the stability window. So the graphite lithium cobalt oxide battery is thermodynamically a nonsense. However, as you know, this combination is at the base of a very successful battery. This because both at the anode side and at the cathode side, we have a formation of protective film. And here is indicated the scheme. You see, here we have, at this side, this is graphite, okay? And this yellow stuff here is this so-called solid electrolyte interface that, a difference of lithium case, is very uniform. Okay? And this interface, this film here, it is not permeable to electrons, so it protects from further decomposition of the electrolyte. However, it allows film, it allows a lithium ion, this gray here one, transport. So lithium ion can go through this film and enter into the graphite and allow the electrochemical process. Same thing on the other side. We discussed that when we will present the lectures on cathode. Same idea. The film is protecting from decomposition because you see there is no electron transport, and allows the electrochemical reaction because there is a lithium ion transport. Okay? However, to have a lithium battery working, we have to form these films. Okay? And this is very important. In fact, all the companies which produce lithium batteries have to cycle the battery 2 or 3 times before putting them on sale, just because they want to be sure that this film is formed. And as we will see, the formation of this film, it results also in some gas evolution. So when we have the formation of the film, we will have some gas evolution. So the producer of the battery has to be sure that this gas is eliminated before sealing the cell. So this formation of solid electrolyte interface is a very complicated and a very critical effect. You can understand that this film protects the battery and the battery then can be wear several times. However, if for some accidental reason the film is broken, it may happen, then there will be immediately some reaction with the electrolyte because we